and share the screen. Okay, so last time we finished here, I guess. So we talked about the concentration of the L2 norm of some Gaussian vectors with independent coordinates. And the idea was that under normalization, basically this guy, the sub-Gaussian norm is concentrated near root n for a vector in Rn. And this is an interesting result. So it says that the distribution is confined to a shell at radius root n plus minus O of 1. And we also looked at the L infinity norm of the sub-Gaussian vector, let's say with parameter sigma I, and argued that basically this L infinity norm is bounded by sigma root log n with high probability, where sigma is the maximum of the sub-Gaussian norms. And I also mentioned something about the expectation, which actually is on the next slide. So I'm going to delete this and actually talk about this. Okay, any question about the previous results that we talked about? So let me just continue with this example, the L infinity norm. So here's a formal result, which has the advantage of not involving this extra gamma parameter. So there was some discussion last time of, so there's a trade-off between what you put here and what you put in the probability part. And so you can choose let's say, for example, gamma in this case is arbitrary. So you can state a result about the expectation, which just avoids these tuning parameters, let's say. So assume that x1 up to xn are zero random variables and they're sub-Gaussians with parameter sigma, let's say each. Or sigma could be the maximum of the sub-Gaussian parameters. Then the expectation of the maximum of them is bounded by root 2 sigma squared log n. Okay, so this is not necessarily the absolute value. But once you have this, you can also apply it to the maximum xi's and negative xi's. So you'd have two n variables, and a similar result will hold. And this is one of the homework problems, exercises in HDS. And so you can get the similar bound with an updated constant for the L infinity norm. Okay, so how do we prove this? Has anyone looked at the proof before, or suggestions of how to prove this? No one wants to make any suggestions. Okay, so this is an interesting trick. The basic idea is
this was the homework exercise, right?
I guess this is for part of it is a homework exercise, not itself. It's like the depends. We'll have to see. It's for Gaussians, and just double check if it was a homework exercise, you get one for free. But I think the homework exercise has more like parts, or
I see.
It might be about Gaussians, but the technique might be useful. So the general idea is this. So you can see it here. So I can bound the exponential of lambda times the max by the exponential of e to the lambda xi. So why is this true? This inequality.
Because the left part is only one term of the right part, I think.
Yes, you can think of it. Yeah, that's easier to think. So this would be, let's say, equal to, there are multiple ways of saying it, but this would be, let's say, equal to e to the lambda xj for some j, right? And that would be less than or equal to the sum. That's easiest.
I'm still a bit confused because I think this is exactly the same problem 1.4 in the homework 1.
So you're worried about the...
Because I see that is exactly the same problem, right? The problem A, the 1.4a.
Is it problem set 1 or 2?
Problem set 1.
1.
Random variable and you do not need any independence, and that is exactly the same as part A of that.
Right. So I'm giving that for free. Is it due? Is the problem due or not?
Yes, I think Friday is the due.
Okay.
Due thing, yeah.
So you get that for free. Think about the other parts then. So I also mentioned that the other one is basically part B is the infinity norm basically. So actually maybe you can complete the proof as an exercise. Okay, so far it's like this, right? Then what you do is you take the expectation, okay? Does that make sense?
Yes.
So if you take the expectation, there's a bunch of, there's a simple step. So you just write it and then remove it. So e to the lambda z, right, is basically this guy. So this is e, so if you take the expectation of both sides. This left-hand side you can compute. The right-hand side is e to the lambda. So I'm going to compare it with e to the lambda expectation of the maximum. What is the relation between these two? Basically, yes. So let's do this. This is equal to expectation of e to the lambda z. I want to see what is the relation between these two guys.
Yeah, so you will put less than or equal to sign here.
Yes, so that's the Jensen's inequality or Jensen's inequality.
Yes.
And so this side contains what you want, expectation of z.
Yes.
And the other side you can also compute and then try to optimize over lambda. Okay, so I think that's good enough for this, and then you can do it the rest as an exercise. Okay. This is let's say the hint, but it's good to remember the result. The result is that this is root 2 sigma squared log n if you use the subgaussian parameters, and the result is so there's no like constants, unknown constants. Just do it carefully and make sure that the constants are also correct. Then you can remember this is expectation of a maximum of a bunch of subgaussian values of parameter sigma. Parameter sigma is root sigma squared log n, and the key is again the order by which it scales, which is root log n. Okay, sounds good.
Yes.
Okay. Any questions? Comments? Okay, so this concludes, let's say, the discussion of sub-Gaussian, basic, let's say, sub-Gaussian and sub-exponential random variables. We'll keep working with these. But I'm going to now discuss a few other concentration inequalities, which are, I would say, more interesting, because so far the most useful result that we, I would say, have is things like Bernstein or Hoeffding, which control the tails of a sum, or the average of independent sub-Gaussian or sub-exponential random variables, the sums of independent sub-exponential sub-Gaussian variables. So the sum is a linear function and has been studied a lot in probability, but not in statistics, but not everything, or not every quantity of interest is a linear function of your data. And so we want to develop techniques that gives us concentrations for nonlinear functions. And that enlarges the scope of these results greatly. Okay, so let's go. And so what I want to talk about first is something called Azuma Hoeffding. So it's an Azuma extension of the Hoeffding inequality. And for this, I need to take a detour, talk a little bit about Martingales. And I wish I had the poll beforehand, but maybe you can answer in the chat. How many have seen Martingales? Remember what Martingales are? Let's not show the slide, just, yes, okay. Yes, they know. 2 people. I need more people to respond. Just 2. So the rest of you don't know what a martingale is, or don't want to answer. No, I've seen but don't know enough. Yes, yes, not me. Okay, so seems like it's split. Okay, so these are, okay, no, I would say majority are not sure. So these are very useful objects, and it's very the subject of intense study in probability theory. And if you haven't seen them, I like encourage you to take go pick a probability book and read a little bit about them. They're interesting. So the basic idea is that they are one of, I would say, maybe 3 fundamental dependence structures in statistics, in probability. So once you leave IID sequences behind and you want to model dependence, there are different ways that you could do it. One of them is modeling things as martingales. The other 2, I'm not sure, but there are other sort of versions. I've forgotten the categorization, right? For example, the like Markov chains, Markov processes are another way of doing it. Martingales are another way, and I guess what is the third? The third one is like the stationary processes or ergodic processes, things like that. But martingales are useful, important. Maybe one of you that knows about them can comment a bit on what they are. Anyone wants to go?
One way to think about martingales is like if you have some sort of like fair betting system, and like every turn you track your fortune, and so
Yeah.
it's fair in the sense that like your expected fortune doesn't change every day, and this kind of thing is a martingale.
Right. Yeah. So, for example, you have a sequence, and the sequence could be your fortune, and given your current fortune, your future, let's say tomorrow's earnings, the expected earnings tomorrow would be 0. It could be something like positive or negative, but as a random variable, the expectation given the current state is 0. That's the martingale. So formally, if you want to define this, you can actually define them with respect to something else. So I'm going to define it here with this more general setup. So in the language of probability theory, so you start with a filtration. Filtration is a nested sequence of sigma fields. If you are not comfortable with sigma fields, these are generally this is not necessary, but generally you take fk to be the sigma field generated by a sequence of random variables. So sigma k, fk would be sigma x1, x2, ... xk. So assuming we have like an infinite sequence of random variables. And you can think of this fk as the information provided by the first k element of the sequence, x1 up to xk. So intuitively, knowing fk means I know x1 up to xk. I can sort of pin them down. Once I know fk, I know the values of x1 up to xk. Alternatively, I know the value of x1 up to xk, I know fk. That's the information in x1 up to xk, sort of. If you have taken 200b with me, it's equivalent to, let's say, basically, you can equivalently model this as a class of all functions of these variables. So all the random variables that are functions of x1 up to xk, you can alternately work with that class instead of the filtration. Anyways, so we have these are nested. I mean, so if, for example, f1 would be the information carried in x1, f2 would be the information carried in x1 and x2, and of course, the f2 contains f1 and so on. And so we'll say another sequence of random variables, let's say y1, sorry, yk. This sequence, together with this filtration of sigma fields, is a martingale if this sequence is, again, terminology from probability theory, is adapted to this filtration, which means that yk belongs to fk, or yk is measurable with respect to fk. That's the meaning of that notation. Again, if you're not comfortable with sigma fields, you can interpret this, given the f that I gave above, this is equivalent to saying that yk is a function of x1 up to xk. Okay, so once I have x1 up to xk, I can determine yk deterministically. Okay, so yk basically depends only on the information in the sequence up to time k, if you think of the index as time. And we also assume that yk is integrable. So the first moment exists for each k. Then the main property of martingale, so those are like technical conditions, but the main property is that expectation of yk plus 1 condition on the sigma field fk is going to be yk. With the example, so fk, so you can interpret this again as if the sigma field is what I wrote there. This is like expectation of yk plus 1 condition on x1 up to xk. Okay, given the information I see from the other sequence up to time k, what is the expectation of the next move of y, and that would be equal to yk. Okay. So again, in the example that was given, so this could be your fortune, and your fortune on average doesn't change. So if you can think of the difference as your gain, your gain given your future gain, one step in the future gain, given the current the state of affairs is going to be on average 0. And then you can also see that this is a valid state. Again, if you recall 200b, or what conditional expectation means, this is supposed to be a function of x1 up to xk. So when I condition xyk plus 1 onto x1 up to xk, that gives me a new function of these variables. And so this statement is valid because I'm assuming that yk is a function of x1 up to xk. So it makes sense to this expectation, for this expectation to be equal to yk. Okay, otherwise that wouldn't be a valid conditional expectation.
So this also implies that expectation of all the yi's are same, right?
Yes, exactly. So that would be the consequence. It's called the smoothing property or tower property. If you take an expectation of both sides, this side expectation of the conditional expectation would be the expectation of yk plus 1, and the other side would be just expectation of yk. Yes, so the sequence will have identical expectations. Right, but this is, let's say, a weak consequence. The Martingale property is much stronger. Okay, other questions? Comments? Yeah, so the second point is basically what I just mentioned. So that we usually work with this specific filtration, and so it gets, you'd say that yk is Martingale with respect to another sequence if basically the above definition holds for the filtration generated by the sequence X. Yeah, so these are one of the most general dependent structures in probability. Many things would exhibit, many interesting processes would exhibit Martingale behavior or related sort of.
So I have one question. I mean, maybe I don't understand things. So here, x1 to xk and y1 to yk are random variables, right? So
yes.
if yi's are independent of xi's, okay. So So what I'm asking that yi's cannot be martingales if yi's are independent of xi's, right?
That's a good question. Can they be or can they not be?
I mean, they can be if all the yi's are same and they are deterministic, but in general, I doubt. I mean, I don't think, although I don't have a proof, but it seems like they may not be. Because you want that expectation of yk plus 1 conditional, because if yi's are independent of xi's, then expectation of yk plus 1 conditional on the xi's will be same as expectation of yk plus 1, and you are saying it is equal to yk. So yk is a random variable, and expectation of a random variable is a fixed number. So you are saying that the fixed number is equal to a random variable, which means that all the yi should be constant random variables.
Right. So you answered your own question then. That's good. So if they're independent, it's going to be a martingale if it's a constant sequence. Otherwise, no.
I see. Okay.
But this is mostly interesting in cases where they're not independent. And in fact, what usually people do is that y and x's are going to be the same. So you're going to be martingale with respect to this the filtration that you generate yourself. So it would be like x is martingale if the most basic definition is that if expectation of xk plus 1 given x1 up to xk is equal to xk. That's the basic one that people use. Okay. So you have a sequence, they're dependent, but there is this particular constraint. The expectation of the next move is equal to the previous step. Okay, good. Other questions?
So one thing, So is this important that this conditional expectation also depends on x1 to xk minus 1? What I'm asking is that do they also depend on the whole past, not only on the xk but also the
Right. So the
past?
condition is that once you condition on the entire past, the expectation would be the last in the sequence. That's the definition of the mark.
Okay,
Yes, it matters. Yes.
Okay.
Okay. Other questions, comments? Okay, so there are sort of extensions of, let's say, limit theory, like central limit theorems to Martingales, or other sort of interesting results. This I mentioned already, the y could be a martingale with respect to itself, and in that case, it's just called the martingale. There's another property which is called, you could have these inequalities. So these are random variables that are real valued. So you could have the expectation of yk given the past, yk plus 1 given the past could be less than or equal to yk. These are called super martingales. And if the inequality goes the other way, so the inequality goes the other way, it's called the sub-martingale, I believe, if I'm not confusing. This terminology is confusing, but one is called super martingale, the other is sub-martingale. Why it's called like that, you have to consult some probability, like there is a reason for this. But a martingale is something which is both a sub-martingale and a super martingale. So it's a very narrow definition, whereas the super martingale is just saying that, I mean, over time your expected sort of earnings are negative. You're gonna lose. Sub martingale says over time there's like a positive trend. Sorry, or vice versa. Just figure this out for yourself. But the inequality should be correct. So NL1, this is a result which is called the Martingale convergence theorem, which is we are not gonna use it, but it's good to remember. NL1 bounded super martingale converges almost surely. This is a very interesting result, which you can drive many interesting other results from this. So being L1 bounded in this case means the negative part of yk. You could assume that expectation of yk, this is a uniform bound. So the expectation of this is uniformly bounded, but this condition that they wrote is milder. So you just need the negative part of yk, the expectation uniformly being bounded. Then the super martingale sort of almost sure converges, which is an interesting fact. Probably. Okay, so this is like I'm not going to talk too much about this, but if you're interested, take a look at the probability book. This is like a one slide recap of what martingale is. The only property that we care about in this course is this interesting property. And I'm going to use it to drive a concentrating clock. So any questions? Okay, so some examples of martingales. So partial sums of a sequence of random variables are, they form a martingale if the elements are IID and zero mean, let's say. Why? Because, let's say, expectation of, what is the expectation of sk plus 1 given x1 up to xk? This would be the expectation of xk plus 1 plus sk given x1 up to xk. Okay? So what would happen here? Anyone?
The first term is independent of the rest, so it's just an expectation, and then the second term just comes out.
Right, so you get expectation of k plus 1 given the rest, which because of the independence, I can just drop the conditioning, and then I get this sk given x1 up to xk. So this is 0 by assumption. And this, you said what about this?
That should just be sk.
Yes, why?
Because it's a function of x1 to xk.
Yes, so sk is a function of x1 up to xk, and from the properties of conditional expectation, more or less by definition, expectation would be equal to itself conditional expectation. So this shows that the sequence is a martingale. So the sequence of partial sums of another sequence is a martingale respected at filtration J with that sequence. Similarly, you can show the partial products. Let's say if they satisfy the expectation is 1, then this is an IID sequence. And this is interesting in the statistics. Anyone can think why this is interesting in the statistics? Why this object would be interesting from a statistical perspective.
When if you take the log of this, you will get back to the first one. And
Right.
sometimes because expectation is 1, so you will get back to 0.
Right, that's true. But then you have to worry about, I want the expectation of LK, not the expectation of log of LK. You have to worry about that. So you can directly show this. That's okay. I'm not going to go through the details. Do it as an exercise. What I'm saying is that why a sequence like this, partial products, might be of interest in the statistics. So I'm going to give you an example. So LK could be product J from 1 to K, F, let's say 1 of xj divided by F0 of xj. So this would be a likelihood ratio applied to a sequence. So let's say my sequences are J from 1 to K. I have a sequence that's either coming from F0 or F1. This is the null distribution. This is the alternative. And I want to test which one it comes from. I form the likelihood ratio based on a sample size K. That would be this object if they're IID. If they're IID, the likelihood would be a product. So the likelihood ratio process would be and then under the null, so under H0, what is the expectation of LK? The product J from 1 to K. Expectation under the null. What is his expectation? Anyone? So these are the densities.
Yeah, so this will be product of F1, product of J from 1 to n, F1 of xj.
Close, but this would be integral F1 of xj. I would say F1
Oh
of
yeah,
x
yeah. There will be integral.
divided by F0x. So what would be the result? So it would be 1.
1.
These
Yeah.
are densities, right? So these terms are, I don't need the expectation of this whole thing, but yeah, so basically you can see that this holds. Each term has expectation 1 under the null. So under the null, this forms a martingale. just think a little bit about this yourself. That is an interesting example. So the let's say if you want to do sequential testing, you'd get the sequence, the likelihood ratio process, and under the null, it would be a martingale. So these are sometimes called exponential martingales. Okay, and then the last one, which is usually, or the one that we care about in this concept of inequality, is called Doomb's martingale. And this is obtained by taking any integrable z, a single random variable. Integrable means the mean exists, basically. And then form this martingale by conditioning z on another sequence with the expectation of z given the rest. And then you can verify that this is always going to satisfy the martingale property, again, by the Tower property of conditional expectation. So these are special cases. And I believe more or less almost all martingales, or all martingales are, can be.
What are x1 to xk's here? In
any other sequence. Take any random variable z and any other sequence of x1 up to xk, condition z on x1 up to xk. Then yk would be a martingale with respect to the sequence x.
And you can define the correlation like according to whatever we want, like correlation of z.
There is no assumption here. So just z is any random variable which is integrable, and x1 up to like infinity is a sequence of random variables. Condition z on x1 up to xk, take the conditional expectation, that defines a new sequence. That sequence would be a martingale with respect to the x sequence. This is one of the most general ways of constructing the martingale.
I see.
Right? And it's not difficult to show. Just this is a good exercise. Again, exercise, show this, that yk would be a martingale. Just verify the property. Okay?
Okay.
Sounds good.
Mm-hmm.
So I'll wait here a little bit. If you have questions, it's a good time to ask. If you haven't seen the martingales before, the definition looks a little bit tricky, but it's good to have some examples in mind. And here are some basic examples. Any questions, comments? Okay, so now how do we use this to provide a concept of inequality? This is the Azuma Hoeffding sort of result. Suppose I have x1 up to xn, a random vector, and z is a function of these. Okay, so this is a new random variable. This is a function of the vector x. And then I consider the Doomb's martingale constructed from z and x. Take the expectation of z given x1 up to xi, and I'm using this notation to simplify the discussion. E sub I of z means compute the conditional expectation of z given x1 up to xi. So that defines the sequence yi. And then I would look at the difference, the sequence I obtained by taking the differences of sequence yi. So we know yi is a martingale. And this different sequence is called the martingale difference sequence for obvious reason. And I'm going to assume that this sequence, the difference, satisfies this property with the expectation of lambda delta I, given the past is sub-Gaussian. Another way. So delta I given the past is sub-Gaussian, or this conditional MGF basically satisfies this inequality. The assumption is just this. So however you want to interpret this. The way to interpret it, like in words, would be delta I is sub-Gaussian conditional on the past with a parameter which does not depend on the past. So this part is non-random. Generally, this is a random variable, and so an upper bound on it could contain random quantities, but here we are assuming that it's uniformly bounded, not uniformly bounded, but just the bound is non-random, like this. Okay, with some parameter sigma I. And this should hold for all lambda. So one way, for example, to realize this, this condition is hard to verify. One simple way is if delta i's are bounded. Delta i's are bounded, almost surely then this would hold, because we know bounded variables are sub-Gaussian. So we want that. And then the result says that z minus expectation of z is sub-Gaussian with this parameter. Okay, in particular, you would have this tail bound. Z, which is a nonlinear function, necessarily not necessarily linear, general function of x, minus its expectation, have this concentration inequality, which very much looks like what you get from the Hoeffding or general sub-Gaussian concentration. Okay, does this make sense? The result is fairly general and very interesting, but this condition is also quite strong. Okay, questions about this statement of the result?
I mean, what is the interpretation of this condition 3? Because you have conditioning also from x1 to xi minus 1. So what is the interpretation of that?
I don't have a good interpretation. It's just what you need for the argument to work. So delta i's are, so if you look at this, delta i's are zero mean, conditional on the past. This is the Martingale property. Okay, so why is this true? Expectation sub I minus 1 of delta I is 0. Can anyone tell me why?
Yeah, because all the yi's have the same expectation.
No, this is more than that.
Oh, it is more than that.
Yes. Anyone wants to comment on this? It follows from the Martingale. It's just equivalent to the Martingale property. So expectation of this times delta I is just expectation sub I minus 1 yi minus yi minus 1. What is the next step?
Just use linearity. And
Yes.
then one of them is dependent on, or one of them is measurable with respect to I minus 1, and the other one you use the Martingale property.
Okay, which one is measurable?
The earlier one is measurable, I minus 1.
Right, both are measurable with respect to I minus, oh sorry, the second one is actually measurable with respect to I minus 1. So this is going to be I minus 1, yi minus 1, right?
Oh, sorry, by earlier I meant like earlier in the process, but.
Right, okay, yes.
Yeah,
yes,
the second.
okay. Yes, the second term is, so yi minus 1 is a function of x1 up to xi minus 1 by definition, and it's going to be, when you condition, it's just going to be itself. And this guy by Martingale property is going to be I minus 1. So the result is 0. Right, so that's why it's called the Martingale difference sequence. So a Martingale difference sequence is a sequence that has this property that this conditional expectation is 0. Okay. If you do it to any Martingale, this difference sequence would have this property. This is the Martingale difference property. So these are zero mean random variables, and so they can at least conditional on the past, they're zero mean. And then you can think of them as like ask whether conditionally on the past they're sub-Gaussian, and this is assuming that. assumes that these differences conditional on the past, they're zero mean subgaussian variables. But the issue is that the subgaussian parameter, that's not a necessarily bad assumption, since subgaussian variables are fairly common. The difficulty is that once you condition, the subgaussian parameter could depend on the past, or could depend on x1 up to xi minus 1. That would be a more, I would say, general assumption. But that would prevent this argument to go true. So we're assuming that the subgaussian parameter is fixed, non-random. That could be true if I know a hard bound on delta I. So I know delta I, let's say, our absolute value is less than 1. Then I know that once I condition, they can't sort of be bigger than 1. They're going to still be less than 1. And so this other side is going to be, the subgaussian norm is bounded by, or subgaussian parameter is bounded by what we calculated before. So let's say b minus 1 squared over 2 or something like that. Or 8, I forgot. Okay, questions? Well, any other questions?
Yeah, I have one. So how did you write expectation of I minus, like expectation of y I minus 1 condition 1 up to I minus 1 is equal to y I minus 1?
The
Like
first term here or the second term?
the second term here. Yeah, why is this?
So, do you, who answered this? David? Was that you? So do you want to mention? Yeah.
Yeah,
What?
so yi minus 1 is measurable with respect to that. So it's a function, ei minus 1 means that we're conditioning on all of the information up to time I minus 1.
Yes.
And yi minus 1 is a function of that information.
Oh, so it's a,
Yeah, by definition, yi minus 1 would be, so this is just going to be some g of x1 up to xi.
yes.
So I minus 1, this is going to be some g of, sorry, this would be up to xi. If I want to be precise, this would be gi of, and this would be gi minus 1 of x1 up to
xi minus 1.
minus 1. So it's a function of whatever you're conditioning on. In other words, it's measurable with respect to that, and so it comes out as so.
I see. Okay.
Yeah.
Okay. Okay.
Sounds good.
Yeah.
Okay.
Thank you.
Okay, so let's see the proof. Maybe it becomes clear where the conditions come from. So let xi or xj be the sequence of partial sums of these, this Martingale difference sequence. And again, you can easily verify that Sj only depends on x i's from 1 to j. So up to the information in the sequence x up to time j. That's not hard to see. So again, this notation, I'm going to use expectation sub 0 here to just mean expectation of unconditional expectation. Okay. So if you look at the, so E sub 0, that's my definition. And E sub n, which is condition everything, of z would be equal to z. Okay, so why is that true? Why is the second one true? So recall that c is f of x1 up to xn. Anyone who hasn't answered, maybe one, two.
Yeah, so this one is the same explanation as what David gave earlier for that.
Okay,
thing, right?
yes, so this is a function of x1 up to xn. We are conditioning on, so at the sub n here means we're conditioning on the information up to time n. Actually, it's just all the time that we have. So we are conditioning everything, so this is a function of those, and just comes out of the conditional expectation. So if you do like a telescopic argument, the S sub n would be this, would be it seems like this is not the right thing. So what do I want to say? Is this the right statement? Is this equal to z minus expectation? This doesn't seem right. It does seem right. Okay, so what is S sub n?
S sub n is yn minus y0, right?
Right. Is this statement true? So this would be anyone knows whether this statement is true or not? So this would be equal to yn minus, so delta I is just yi minus 1. So yn minus y0, and then you have to interpret y0 as, so y0 would be expectation 0, which is just the expectation of z. So this would be, this quantity is equal to this. The claim is that this other one is equal to this. Is this true?
Yn is expectation of z condition on all the xi's, right?
Right. Which is, again, by the same argument, it's going to be equal to itself. So yn is, you have to modify this. We don't need the other thing. So it's just the explicit expectation of z conditional x1 up to xn. And we know that z is dependent on x1 up to xn. So this z comes out. Okay, so we didn't need this statement. This is,
so
this one.
Why did you, so why did you assume that z is a function of x1 to xn?
Because that's what I want to
Okay.
control.
So that is
Right.
the assumption. Okay.
Yes.
Okay.
Okay, so yeah,
Got
we
it.
don't need this. Just directly follow. So yn minus y naught is equal to Sn, and yn is equal to z. And okay, so the bottom line is that this is true. Okay. So what I've done is that I've written the difference z minus expectation of z as something that looks like a sum. Okay. So now I'm probably in business. So I know how to deal with concentration of things that are of the form of a sum. So I have managed to write this as a sum of a bunch of random variables. The issue is that these random variables are not independent, but they have the Martingale difference property, and so we might be able to do something. So the idea is that, okay, so I'm going to take, I would like to calculate the sub-Gaussian. I would like to claim that, for example, Sn is sub-Gaussian, basically, right? So we want to claim this is Sn, and claim that this is sub-Gaussian. Now what I'm going to do is that control the MGF condition on the one step in the past. So e to the lambda Sn condition on everything in the past, n minus 1, sort of 1 up to n minus 1. let's do it maybe separately somewhere more. So how do we control this? Expectation of e to the lambda is n. Okay, one step in the past condition like that. I would write this as expectation of e to the lambda Sn minus 1 plus lambda delta n. Okay, Sn is a sum of these things. Remember, so Sn is just sum I from 1 to n delta I. So what is the next step?
You can break it up and then use the assumption you had about the properties of the delta n's.
Break it up how? So I can do this. I know this much, so the rest you should help me. So this is still different than this. What can I do here?
The e to the lambda Sn minus 1 is now like a constant, so you can pull it out, right?
Right, so it's measurable with respect to, or function of x1 up to xn minus 1. So it comes out of this conditional expectation as itself. So I get this. Now I'm assuming that this is another random variable, but I'm assuming that this is bounded by e to the lambda sigma I squared. You can see it up there, divided by 2, right? And so this whole thing is e to the lambda squared sigma I squared over 2 e to the lambda Sn minus 1, which is nice. Okay. Then I would do the same. So this is determined. I care about the next term, so I'm gonna do this another time. So and condition on one step in the past of this, and then you can verify that this would be e to the lambda Sn minus 2 comes out, and e to the lambda squared sigma I squared. Sorry, this should be sigma, not I, sigma n. This would be sigma n. This would be sigma n minus 1. Okay. And can I combine the two somehow? Combine these two? Can I determine this? E to the lambda Sn.
Yes, because you can use the tower property.
Right, so this would be e to the n minus 2, and then e to the n minus 1. So conditioning on this sigma field, which contains this one, doesn't affect. So I'm gonna always, so when you condition on two nested sigma field, let's say, right here. So expectation of, let's say, x given f, and then expectation given g is going to be expectation x given the smallest of the two. I'm going to write it as, so suppose f contains g, or the other way around here, f, g is the smallest one. G is contained in f, so this is going to be g. Okay, so I'm conditioning on the bigger one, and then conditioning outside the smaller one, I get the smaller one. Any case, so this verify for yourself. This if you have taken E200B, this was a homework problem. So what you get here is this is going to be bounded by, so conditional expectations are monotone, so this is going to be bounded by thing that we had here, right? You get e to the lambda squared sigma n squared over 2, e to the lambda sn minus 1. The constant comes out, you get e to the lambda sigma n squared over 2, and then e n minus 2, e to the lambda sn minus 1, which we've computed here, as we have a bound here for this. And so we get this is bounded by e to the lambda squared sigma n squared over 2, e to the lambda sigma n minus 1 squared over 2, e to the lambda sn minus 2. Okay, and then we can peel away each layer like this, and in the end you end up with e to the 0, e to the lambda sn minus 1, right? Let's see. This is not right. Yeah, so I'm not going to write it down. So this is, you end up with this, e to the 0, lambda s minus 1, and then you get all these exponentials. So here we have 2 of them. Keep repeating this until you get to 0, and this would be 1, and then you have like accumulated all these terms for all of them, right? So you end up with this result. Okay. So what is this? This is just the expectation by definition. This is expectation under 0 is just expectation. So this is the MGF of Sn. So we've proven that the MGF of Sn satisfies e to the sigma squared lambda squared over 2, and so it's sub-Gaussian in this parameter. Okay, you see that the proof is straightforward and clean. It's just using this conditioning and the idea of the. So this is actually the only part that we use the fact that this is a martingale is to make sure that this is going to satisfy, basically. Because this requires at least that this guy has conditional 0 mean. Otherwise, it can't be satisfied. But we didn't really use martingale property directly. We just used this. And basically, the idea behind the martingale construction is just the proof is based on conditioning. Okay. And the martingale property indirectly was used through this, which only holds if delta I is a martingale difference, but requires more than just being a martingale difference. Okay, any question about the proof, the statement? Questions, comments? Okay, we spent too much time on this. Let's move on maybe fast. This is a very interesting result, but as I mentioned, there is a condition which is difficult to verify. So satisfied if delta I is bounded, let's say, almost surely. Okay, or it could be in an interval. You can verify for yourself. This is the easiest way. So if you have a bounded martingale difference sequence, and this leads to this property that I would say this second inequality, which is called bounded difference inequality, which really is a consequence of Azuma Hoeffding bound. But it also has like McDermott's attached to it, so McDermott's inequality. I think it's a proof that I'm going to give you is just makes it a consequence of the Azuma Hoeffding. So you say a function of x1 up to xn. This is a deterministic function. This function has the bounded difference property. If I, whenever I perturb one of the coordinates while keeping the rest of the coordinates fixed. So this part is kept fixed, and I perturb the I coordinate, the absolute value of the difference is bounded, let's say by Li. And the bound is uniform over the space, so it doesn't matter which sequence I choose. So the Li does not depend on the sequence. Okay, so uniformly have uniform bounded difference property or bounded difference property. Okay, if a function satisfies this condition, and if xi's have independent coordinates, again, notice that I did not use independence here, which was interesting. I did not assume that x1 up to xn were independent. Okay, but now I'm assuming that x1 up to xn are independent, and I'm going to also assume that f satisfies the bounded difference property. Then the f minus expectation of f is going to satisfy this deviation bound, which looks like Hoeffding bound with this parameter going on there. Okay, so it satisfies the sub-Gaussian tail bound, f of x minus the expectation of f of x. Okay, does the statement make sense? So let me show you. I'm going to give you a proof which gives it with a force constant, and there's a better bound which is not really that much difficult, but I think this is more transparent, but the constant is worse. You can read the other one yourself. So to prove it, I would take in from Azuma Hoeffding and define this function, gi of x1 up to xi, to be the expectation sub I of z, because z here is our usual thing. So z is f of x1 up to xn. Okay, and expectation sub I of z is just expectation of f x1 up to xn given x1 up to xi. Okay. So this shows that okay, so this is just definition. So I can define this to be gi of x1 up to xi. Okay, so this would be a function of x1 up to xi, and the particular function could depend on I. So I defined it to be gi. Let's say this is defined almost surely, but for our purpose, we're not going to worry about almost sure. We're not going to attach almost sure, but this is almost surely defined, like almost everywhere defined. So we're going to prove that gi has the bounded difference property. How do we show that? So the trick is so how do we show the bounded difference property? I want to show that gi also satisfies the bounded difference property. So if you look at this one, I'm gonna anyone can tell me how to show the bounded difference property for G? So let's not worry about that. I'm gonna maybe next time, or you can think of it. But the idea is that if F satisfies bounded difference inequality, G is going to satisfy the bounded difference property. Just verify that for yourself. This requires the independence, sort of. But let's assume that that's also true. Now I'm going to look at my Martingale difference. So Martingale difference is delta I. It would be expectation of Z under I, and then expectation of, so this would be, so I'm skipping the part that we show that GI is also satisfies bounded difference. But so this is equal to this by definition. That's the Martingale difference. And the second term is equal to this guy by the Tower property. And so the first term here is just by definition this. And the second term now, if I replace this guy, again, by definition would be this. So I'm basically looking at GI of x1 minus, sorry, up to xi minus its expectation conditional on the past. Okay, so now I would like to show that this guy, basically this Martingale difference, conditional on the past is bounded. So let x prime I be an independent copy of xi. And then if a condition on the past, intuitively what I can do is I can sort of fix these, let's say at certain values. Let's say intuitively what I'm doing is think of setting this equal to x1. This is like back of the paper calculation. So set them equal to fixed numbers. Then this guy would turn into this. And this guy basically conditional, when you want to find the conditional expectation, will be equivalent to setting these to be constant and then taking the unconditional expectation with respect to the last variable, where I replace it with a copy of x. Okay, so this part requires some thinking why this is true. But this is basically true, this one, because this is sort of the Fubini result, or the generalization of the Fubini result. It's saying that because of the independence, once I condition on x1 up to x minus 1, the distribution of xi conditional on the past does not change. So it would be just as if I replace it with an independent copy and then set them equal to constants, and just basically take the integral with respect to the last coordinate. So the fact that this is more or less this, you have to argue for yourself. This follows from the independence of this collection. But now, if I have that, then I can use the bounded difference property of G. Sorry, we're a bit out of time. I'm trying to run here. So this is going to be I'm going to do for simplicity. This is going to be bounded by, I could take the expectation out and I would get the expectation, and then GI of x1 up to xi minus 1, and xi, this is capital XI, minus GI of x1 up to xi minus 1, and xi prime, absolute value. Okay. And by the bounded difference property, because these two functions only differ in the last coordinate, this is going to be bounded by Li. Okay, so I have managed to show that this condition holds, this holds condition on x1 up to xi minus 1. And so this conditional NGF in the Azuma Hoeffding is going to be bounded by this, where sigma I squared is just 2Li squared over 4. This is the thing that we showed before. So if you have a bounded variable, it's sub-Gaussian with that parameter. So this is basically going to give you a tail bound like this, e to the negative t squared over 2 sigma squared, which is going to be sigma I from 1 to n Li squared. So this is worse by a factor of 4, but it's basically the same bound. Okay, and then there is a better argument on the next page that you can read. Okay, so the last part was a little bit quick. If you have questions, you can either ask now or maybe at the start of the next lecture. Was this more or less okay? Comments, questions? Okay, I'll upload this. Maybe you can take a look and you can come back, and if you have questions. This is basically an application of the Azuma Hoeffding, but there's a tricky part where you have to basically do two things. First, show that GI has bounded differencing property, and also there's a bit of trickiness going on when you try to control the absolute value of this. But the basic idea is that this martingale difference sequence that you get out of this is bounded, and then you can use the Azuma Hoeffding. Okay. Okay, so no questions it seems. So let's stop here, and thanks for listening. And I'll see you either in the office hours or next week. Okay. Yes, the proof was clever. Yes, what a clever proof, right? Just think about this. It's a very interesting proof, and the result is very interesting as well. Okay. Questions? No other questions. Okay, so see you guys next time, hopefully.
Thank you.
Thank
No
you.
problem.
Bye-bye.
You're welcome. Bye-bye.
Thank you.
Thank you.
Bye-bye. No problem. Bye-bye.